This is Module 12, Lesson 3. We have another very brief lesson with no practice attached. This time we are going to talk about sound. Sound is, of course, made up of waves. So sound is made up of longitudinal or compressional waves. What they do is they hit our eardrum and it, creates a signal that's sent to our brain. The vibrations of it sends a pattern to our brain, and we interpret that as sound. Now, the speed of sound depends on its medium. I gave you some information here about that. Basically, sound will travel faster in solids than in liquids and faster in liquids than in gases. So as your state of matter changes in general, the speed will change. It's the fastest in solids and slowest in the gases. The density and the elasticity of the medium also affect the speed, but that gets into a little bit more detail than we really want to go with this class. If you would like to look up some of that, you can. Pitch. Pitch is how you hear a sound. It is like like how high or how low, and that is determined by the frequency of the sound wave itself. In the first lesson, I think it was, we were looking at some examples about musical instruments playing a musical note as a certain frequency. That's exactly what determines how you hear those notes, is the frequency of the wave makes it sound higher or lower. Volume is determined by the amplitude. Volume is just the loudness of the sound. So the louder the sound gets, the more energy is being put into it, so the bigger the amplitude of the wave would get. Now, the Doppler effect. This is pretty cool. I am going to link some videos of this for you through YouTube for you to watch. So make sure that you watch these couple of examples. They're not going to last but just a minute or so a piece. If you've ever noticed a car going by you with the horn honking, it doesn't sound the same the whole time that the car is passing you. If you've ever stayed still and the car honks the horn, we're going to imagine that waves are coming out of this car, and this is going to be super ugly because, unless it gives me the option of shapes, because I'm going to be drawing circles and all I can say is laugh at me. That's all I know to tell you. So if the person here in the car, they honk their horn and the noise comes out here, what's going to happen is those waves are going to come out and they're going to travel. And they're going to travel out from the car, and I did not mean to make that look like that on the bottom. I just need to make enough of these that we can see. Try not to get frustrated with me. I'll try not to get frustrated with myself, and you don't get frustrated with me either. I don't know why I can't make them lower on the bottom. So those waves are going to come out, and they're going to travel in a circle. Mine is a very smushed circle. But my intent is that they be approximately equal distance apart from each other as they're coming out of the car. If you just stood here, you're standing here listening to this car honk its horn with your very long torso, you are going to hear the same honk the whole time. The horn is just going to be one big sound. Now, what if the car was moving at you while honking its horn? Maybe it wants you to get out of the way because you are standing in the way. And thankfully, the car is not going to run you over into a splat. It's going to go past you. So you are safely standing off to the side of the road. You live through this. So our car is going to travel by you, okay? What's going to happen is this, is as the car basically is coming at you, what it's going to do is it's going to actually push together the waves in the front of this. I do mean this to look this kind of distorted. I want my waves to be closer together on this end and farther apart on the back end, because it's almost like what it's going to be doing is pushing the waves closer to each other on the right hand side. Well, what does that mean for sound? That means on this side you are going to have a high frequency. You're going to have low wavelength. It means that the pitch is going to be high too, because if you have a high frequency, then you are going to end up with a high pitch, okay? As it goes past you, all right, once the car is beyond you, what's going to happen is you're going to be on this end of things. So the waves in the back are going to be really stretched out further apart. Excuse me. They are going to have low frequency. They are going to have a big or a long wavelength. And then they're going to have a low pitch. So the waves in the back are going to be represented by this. The waves in the front are going to be representative of this. So what you're going to hear is a very high-pitched noise coming at you and a lower-pitched noise going away from you. It's ambulances, fire trucks, anything that makes any kind of noise as it goes past you will be higher pitched heading towards you. So it'll be high pitch here. And then once it passes you, you're going to hear the low pitch. And it's because coming at you, you're on this side of the wave, and after it passes you, you're on the back side of the wave and you get the spread out part. It's called the Doppler effect. It's this being able to push them together on the front end and like spread them out on the back end. Now, what does it have to do with anything in physics? It's really cool as far as how this is used with light. We can use it to study distant galaxies. We can use it to study things in space. And what we can see is that they're shifted towards the red side of the spectrum. Why is that? Well, think about what we said in the previous lesson with our reference table. Our colors of light were Roy G. Biv. We said red has the low wavelength, and if it's got what I mean by low wavelength, it's got a long wavelength. Wavelength is big. I don't mean that it's I probably said that backwards by saying that it's slow. It's got a long wavelength. It has the most lengthy wavelength. And then this one is going to have a shorter wavelength. That means that this will have higher frequency and this will have lower frequency. So this would be representative of which part of our wave here. If it's got a longer wavelength and a lower frequency, then it is representative of the waves in the back. Okay, because you remember if things are, let's see how well I can do this, moving away from us. My circles on this thing stink. I'm sorry. I need like a circle tool. As it's moving towards you, things are smushed. Moving towards you, you had little wavelength, high frequency, and moving away from you, you have big wavelength, and we have low frequency. So what we see, if we see red, if we're shifted towards red, then what that means is we're looking at the back end of the waves. It would indicate that things are moving away from us. And it's how scientists have come to the conclusion that the universe must be expanding. But they use the Doppler effect in order to do that. You can have blue shift. If you saw blue shift, then what that would indicate is that something is moving towards you. Now, there's a whole lot more to this than what I'm explaining, so feel free to do some Googling and go a little bit deeper with this if you'd like to. I just want you to know an example of how this is actually used to study something other than sounds, and be ready to see those YouTube links that I was going to give you to experience the Doppler effect yourself with a car horn honking as it comes towards you. Don't try it on your own, please. Just use the YouTube video. Now what? Again, there's no practice for this. Just make sure that you understand the concepts, and if you need help with anything, please feel free to let me know. I'll be available.